going to derive what we're going to call a transfer function. Okay? So transfer function is you have some input and some output of your circuit. So in this case, our input is our voltage source, and our output is our capacitor voltage. And we want to find this transfer function. Why? Well, the transfer function, right, you can use it as like a map, right? Any input signal you put in, whether it's the wall voltage, a vuvuzela, me talking, you can take the signal you want, and you can use the transfer function to figure out what the output will be. So all you do is you take an input voltage with its own magnitude and phase, and you end up with an output which will be the product of the magnitude you put in and the magnitude of the transfer function at that frequency. And the phase will shift a little. So you'll have the original phase plus whatever the filter or the device wants to do to it based on the frequency, right? And the key thing here is, whereas before, we'd have a number here like 3 and like 5 or something, now it's going to be a function of the omega. So if you want to know how a particular signal reacts, you can plug in that omega. So what we'll find is that the output is going to be scaled and shifted in time, and how much scaling and how much shifting are going to depend on what you put in. The frequency, on the other hand, though, will be unchanged. There's a property of linear systems, and so when you have nonlinear elements like diodes, that won't be the case, but for everything we're doing so far, linear is good. And basically what you get, tell you how to respond to any frequency. So this is a thing you may have heard of in 20 or elsewhere called the frequency response. So if you wanted to use the frequency response in the most obtuse way, you could figure out how will it respond to a 3 cosine 52 plus pi 4 signal. So all you would do is you would basically figure out what are the magnitudes of you write your signal as a phasor, your frequency response as a phasor, and this is kind of where you're using the transfer function. As you're saying omega is 50, okay? If omega is 50, right, then you can combine them. At 50, what the circuit's going to do is it's going to scale down your signal by a factor of root 26, and it's going to try at that frequency to make it delay by 1.37 radians. So if you'd like, if you want to find what the actual phasor is, you just multiply it. Like, there's all the stuff we've been doing, and what you'll find is the final signal, which is scaled by root 26, and it's delayed by 1.37. Okay, so that's sort of like the most obtuse way. Like, I want to know how does it respond to the signal. Now, in practice, you'll never do this because you're not going to want to know like how does it respond to this necessarily. And so we usually think of it more generally, right? You just plug in some omega, same kind of deal, right? And so this overall function, right? Like the overall circuit, if you'd like, as a function of the omega, is it's going to scale by the magnitude of the transfer function of that frequency, and it's going to delay it by some amount, which is based on the frequency of the signal. Okay? So hopefully that makes sense. What does it mean? Okay, good. I'm glad, right? What does it mean? Well, it means that if you pick, so let's go back, right? So as we were saying, this is a good question. Okay, yeah. Sorry, so I'm in like slightly speed mode, so I apologize for blasting through. We're good though, actually, we have time. It is a hard lecture. It's a tough one. All right. I think last one's harder maybe, but or the previous one. But yeah, okay, so what we've got here, right? Let's think about what happens to the signal overall as a function of omega, right? So if omega is really small, right, what will happen to the size of the cosine? That's sort of question one. So the size, this has nothing to do with the size. It's inside the cosine, right? So all you got to think about is this thing, right? Well, if it's 0, let's say, it's the smallest it could be. Then the whole thing will just be what? 3, right? And it started at 3. So if you'd like the scaling factor, right? This is how much it scales by, this red number. The biggest it can be, because it's a passive filter, is 1. So when omega is 0, it's just locked in where it started. And as omega gets bigger, the cosine is less and less able to show itself at the capacitor, right? So as if omega went to infinity, basically you would see kind of like, if you were in lab and you had like a setup which was showing you the capacitor voltage and you're tweaking the frequency of the knob, you would see it like, matching. And as you tweak the number, you would see it get like, tighter and tighter, like the oscillation would be faster and it would get smaller and smaller. You left it at the same scale. Now at the same time, this delay thing would be different. So what's the arctan of 0 over 1? So geometrically, again, like if you want to think about what an arctan is, look at this. So you kind of got your real over your imaginary. So what's 0 over 1 going to give you? Yeah. And if omega got really gigantic, what would it give you? Oh, it would go up, but so it's a minus, right? So let's see, like, well, I'm going to show a plot again in a second, but basically you can see that as this gets really big, right? Like geometrically, this number should approach pi over 2, so it'll keep delaying more and more. But I think that the next slide should kind of address that. Yes? This is a low-pass filter, yes. So if you'd like, right, let's think about those two things separately. Like the magnitude made sense. That I haven't said, right? So, yeah. No problem. OK, so if you wanted, right, you could think of it this way. This is basically us saying as you tweak the frequency, how does it behave? So the magnitude of your output signal, right, like how much it tries to scale it, as you increase the frequency, it drops off. And on a linear scale, our plot looks like that. But on a log plot, if you do a log-log plot, you get this shape. And I claim this is a lot more instructive, because frequencies can vary really widely. So for example, if you plug in 10 to the minus 2, right, a very slow frequency, it's handy to know that your frequency is basically unchanged. And the other nice thing is that, and we'll talk a lot about this next time, how to read log-log plots and make them. And if you've done E20, it'll be really boring probably. But the picture here is that once you go above some certain frequency, then it's just inversely proportional. Like every single time you go up by 10, your magnitude will change by a factor of 10. So just understand that qualitatively, and we'll do the annoying details later. But basically, this is what your filter does. You put in a low signal, low frequency signal, and you get the same. You plug in a high, and you get a much smaller signal. So it's a low pass, is why they call it that. So hopefully this makes a lot of sense. So phase, so in the context, that's what we just said right here. If you're below some certain frequency, you're pretty much in the clear. In this case, 10. Once you get above that, you're going to get increasingly destroyed by the filter. OK, so phase is a little more subtle and just generally a little less useful, but still important, is this notion of phase. So if you plot arctan on a linear scale, you see that for very small omegas, there's not much of a delay. But then as you increase the omega, you end up getting 180 degrees. Wait, no, 90 degrees out of phase. And if you plot on a semilog scale, and again, I picked semilog, and it turns out it's a useful one. What you'll see is that for very small frequencies, there's no delay in your signal. Basically, if you were to overlap them in time, right, if you showed the V and the I on the same axis, they would be kind of going up and down together. But as you increase your frequency, you end up being out of phase completely. Because it's radians, yeah. 90, yeah, 90. OK, because if you're 180 degrees out of phase, you end up where you were already. But, well, whatever. Yeah, 90. Yeah, it's pi over 2, yeah. OK, so basically, if you look at this plot, right, the idea is that if you have a signal which is like pretty low frequency, the capacitor voltage will move in time with the source. And above that, it'll get out of phase. So this is important because if you have, suppose this was some audio